Okay. So, and then I had a rope, change colors to that, which was, if you want, is wrapped around D, and it hangs down like that. And there's some object called C, which hangs down. All right. And so in the problem, they gave us the different radii for these different things. We are told that D is attached to gear B. So that means what? If two objects are glued together as they rotate.
I said they have the same velocity?
Nope.
Or acceleration?
They have something the same, but it's not their velocity.
Acceleration?
No.
Huh.
The distance they travel, like each point is gonna be the same.
No. The distance traveled by a point on D is different than the distance traveled by a point on B. When these two are glued together, I'm talking about D and B. What do they have that's the same?
Position?
The change in theta is gonna be the same, right?
Theta, yeah, the angular quantities are the same, not the linear things. Okay? So here's the thing. For A and B, they have the same linear quantities, up to a minus sign. For B and D, they have the same angular quantities. Okay?
Like the angular velocity of B is the same as D?
Yep, or alpha or omega or theta. They're all going to be related. Whereas for A and B, it's the linear quantities that are related. Okay, so that's really the key thing you have to know to figure this out. So here's the thing. We know the radii. They tell us alpha for A, and we want the velocity for C at time 3. So we know RA, RB, RD. I think the problem gave lowercase r, so I'll do the same. And we also know alpha for A. And we want V for C. So we want the velocity of this mass. And I was telling Tim, I had a couple examples that I worked out where I struggled. You have to watch your minus signs. So it seems like in the book, they don't always say that the minus signs on the angular quantities are the same as you would do in math class. They kind of flip things sometimes and use a left-hand coordinate system. And so I would just say watch it if you're going through their examples. And I went through and tried it in my case, always choose clockwise is negative, counterclockwise is positive. And it seemed like with one example, which was obviously a typo, every time I went back and computed a linear quantity, like a velocity or an acceleration, we got the same answer. But sometimes our angular quantities were off by an overall minus sign. And I think that's just a choice of convention that they made a different choice. So what I would say is if you draw a picture, if you quote a number and say that say omega is 2 radians per second, as long as you give a diagrammatic picture as to what you're referring to, namely clockwise or counterclockwise, then it's fine. Physically, they're the equivalent. Okay, so that's how I would say. So draw a picture specifying your choice of positive and negative on the angular quantities. And I would say, when in doubt, go with the math definition as far as what's positive and what's negative. Okay, so these are the things that are given, and I want the velocity. So, and they tell me this is some constant. So alpha for A is constant, all right? So that's kind of there. Now, so let's go through the thought process. I know that the linear quantities for A and B are related because basically they roll without, or they turn without slipping. So that means the arc length traveled by a point on A is the same as the arc length traveled by a point on B. Or if you take derivatives, that's still going to be true. So that's going to let me say that the radius on A times omega on A must be up to a minus sign the radius on B times omega on B. Now, I think you have to look at the diagram. The diagram says that A rotates clockwise. So if you think about it, if A rotates clockwise, that means B is going to rotate counterclockwise. But if B rotates counterclockwise and A rotates clockwise, that means that their omegas are going to have a minus sign between them. So one of them, namely A, is going to be negative, B is going to be positive. So I need that. I need a relative minus sign between them. All right.
Sean, for the minus sign, is it for, you said for both of them, or just like for RB?
Well, one of them will be positive, one will be negative. So it doesn't matter where you put the minus sign, but you have to have a minus sign somewhere.
All right. Didn't you do it the same way, and then there was something wrong with the minus signs yesterday?
No, I think that one was okay. There was well, I think it's okay. Let's see here.
Yeah, and then you added like equal RBWD, and then you gave that a minus sign too.
Yeah, I think I just dropped a minus sign. That was a separate issue.
Oh, okay.
That was a separate issue. Yeah, so let's go through. Then what I know is that I know that the velocity of C has to be the same as the velocity of a point on this edge of this wheel. So that tells me, okay, before I do that, because B and D are welded together, I know that this is minus RB times omega D, because D and B have the same angular quantities. And then I know that the velocity of C has to be the radius of D times omega for D.
Mm.
All right. Now let's worry about minus signs here. Let's make sure I've got this right. Omega for D will be positive, and I'm expecting the velocity for C to be positive. Okay, so that makes sense that I've got a plus sign here.
So you're gonna replace VC in there, back in there? It will be negative VC?
Well, I'm going to work out a formula eventually relating VC to omega A. I think what happened is that when I substituted in, when I actually put in the numbers for omega A, I put in positive numbers, but actually I should have put in negative numbers to make it work out correctly. So what I'm trying to solve for is this. So the logic is going to be to solve for omega D using this relationship, plug it all in, and then I end up with omega A here. So this is going to be minus RD times RA over RB times omega A. So all I'm doing is solving for this and substituting into here.
WD.
All right. Is that, raise your hand if that makes sense, how I got to
Uh,
that.
Sean, I just don't get wait, how did you solve for WD if there's like 3 equal signs?
Well, they're all three equal. So what I did is I solved, I guess I solved this equal to here. All right, play with the algebra, Mohammed. But that's all I did was set this equal to this, solve for WD, and substitute.
Oh, okay.
All right.
Like one
So
of them equal to another, and then you solve for WD. Okay.
Yeah.
So
Okay.
I know, like, why doesn't is it just because we're like assuming the block has no mass or something? Because wouldn't the mass usually affect this?
Well, right now we're doing kinematics.
Okay.
Next chapter is torque. So, and moments of inertia and mass and stuff. So right now it's like in physics 1 where we just said, I don't know why, right? In kinematics, you're just given an acceleration, or you're just finding an acceleration and describing the motion. In dynamics, you are actually explaining why with forces. Right now, we're just describing the kinematics of it, and then next chapter we're going to relate it to torques and things.
Okay.
Yeah. All right. So I have to solve this equation. So I've got numbers here for all the things. RA is 75 millimeters. RB is 225 millimeters. RC is 125 millimeters. And then my formula says VC, and alpha, sorry. Alpha, and I think this is where I went wrong in the presentation. I had this wrong by a minus sign. Alpha A, the way I've drawn it, alpha A should be negative 4.5 radians per second squared. I think I had a plus sign there. So then VC, when I plug it all in, is going to be 125 times 75 divided by 225 millimeters. They all have units, so that's fine. And then I get minus. So okay, there are two things. I had a minus sign from the formula. There's an overall minus sign, and then alpha itself is, sorry, dang it. So I jumped the gun. I need omega for A. Okay. Now, how do I find omega for A? Because alpha is constant and it starts from rest in the problem, I know that omega for A is just alpha for A times time. And it starts from rest, so that's it. So I can just substitute in here alpha, which has got a minus 4.5 radians per second times the time, and they tell us to find it at 3 seconds. So I multiply all that out, and this should be seconds squared. And so I ended up with positive 562.5 millimeters per second. So, Mohammed, you were asking about a minus sign. I think when I first did it, I didn't put this minus sign in when I substituted in numbers.
Oh.
And so I was off by a minus sign. Okay. So that was the example I was trying to do. Can everyone read that? Hopefully it's okay.
Yeah.
Okay. All right. let's erase that.
Are we gonna have to like use gear relations? Like if one is bigger or like one turns more turns than the other, like what we use in strength of materials?
Yeah, I mean, but that should be, all that's saying is that the arc length traveled is the same,
Mm-hmm.
right? So if I have two gears, you know, whatever, with radius R1 and radius R2, I know that the distance traveled by one equals the distance traveled by two, which tells me that R times the change in theta for one equals, sorry, R1 times change in theta 1 is R2 times the change in theta for 2.
Mm-hmm.
It just tells me that the change in theta of 1 over the change in theta of 2 is going to be R2 over R1.
Mm-hmm.
Okay, and that's just going to be up to a factor of 2 pi. That's just the number of turns 1 over number of turns 2. Isn't that what you get in strength of materials or wherever you're seeing that, where the ratio of the number of turns is the inverse ratio of the radii?
I think we got like it's two. It would be two for theta. It would be 2R1 equal 1R2, like one rotation of R2 or something.
What?
Hold on. I'm trying to.
I'm not gonna lie, I have no idea what's going on right now.
Well, Muhammad's
What are you
saying
guys talking about?
he's just trying to relate the ratio, the arc length travel. Well, the number of turns of one wheel to another, that just comes from requiring the distance traveled by the point of contact is the same.
Okay.
I have to check it again.
Yeah. All right. Let's kind of regroup. We kind of went off track a little bit from what I was wanting to do. Let's go through. There's a group problem, and what I want to do is break you guys into groups, and I want you guys to try to solve it. And so I want you guys to try to solve it, and then we'll go through the solution together. Okay. All right. Let me do that. To breakout rooms. So first off, I'm going to share the problem on my screen. All right, and we'll do slideshow. So the problem I want you guys to think about is this one. Here's the problem. Okay, so there's some sort of a gearbox, and you've got these two gears. All right, and you guys so you might want to write these numbers down and get a good picture of this. And you're given that gear A has an angular acceleration of some number. It is not constant. It changes in time. So alpha grows cubically in time. And they tell you the initial angular velocity for A is 20 radians per second. And the goal is to find the angular velocity and angular displacement of B when time equals 2 seconds. Okay. So You're trying to figure out what is the angular velocity and the change in theta for gear B. All right, I'm going to, while you guys think about that, write all that stuff down. I'm going to break you into groups, and we'll try that. So, 2. Okay.
So Sean, like a problem like this, would you start it similar to like we did the last one, like setting up the relationship between?
That's
Uh,
exactly what I would do. Yeah. Start with things that you know. You know that the arc lengths have to be the same. Right?
so when
Start
you say
with,
that the arc lengths have to be the same. Is that where you say like the radius of A times the omega of A equals
Yep.
like negative? Okay.
well, okay. So the arc lengths have to be the same. And then basically write arc length as r times theta, and then start taking time derivatives. But because the radii are constant, that's how I would do it. All right, so tell me what you guys are seeing. Can you guys see each other as a group? I don't know how it works to you guys.
I can't really.
I don't
No,
think
it hasn't
it
changed.
seems like nothing has changed, honestly.
Well, okay. If I do move to exchange. Have you done this before, Tim?
I've been in a meeting where it was done before, but I've not done it myself.
Allow participants to return to the main session. Move all participants into break room.
Sean, are you talking about the thing where we like write on your like board or something?
No, I'm talking about you guys should be able to chat with each other. I just said move participants automatically.
So what it does is it breaks this one Zoom meeting up into a bunch of little Zoom meetings where you'll be with just your partner.
Yeah.
And you can talk one-on-one that way. I'm sorry, Sean, I'm not going to be a help there and understand how to do that. With my subscription, it wasn't an option, but until maybe the JCC stuff was added on, you're seeing that option, so that's obviously available to you, right?
Yeah. So nobody's in a room. That's so bizarre. Like I've assigned you guys all to rooms, but it's not.
Who's my partners, John?
Well, that was the joke. I didn't put you with one. Well, let me try. So if I click on Thomas, I should be able to move you to here. So Thomas, I just moved you to a group. Did it change anything?
No, I don't think so. Nothing looks like it's changed.
All right, I don't know. I'll have to play with this more. This just fails. All right. Well, I will just get rid of that idea then. I even watched the Zoom video on how to do this, and they said you just click, 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 and it just goes. All right. Well, all right. So let's go through this then. What are the things we know about this problem? I'll leave it on the. So you guys can still see the my slide.
Yes.
All right.
Yeah.
Yep.
Okay. So just take a second, start working on it. I guess on your own, and we'll. Yeah.
Sean, on the book, there's on page 327 procedure for analysis for anyone if they want to use it. It has everything like the steps and the formulas.
Yeah.
If
Okay.
anyone is interested.
But I mean, okay. I think this basic strategy would be to write down and what happens when you what saying. So you want to say that the arc lengths traveled by the point of contacts are the same.
Mhm.
And you want to start taking time derivatives. So that's going to say R omega of one of them is related to R omega of the other, and the same way with R alphas. And then you have to use the fact that alpha is not constant. So that's going to tell you something.
So for instance, so like when you get to the point where you have like RA WA equals negative RB WB. So when you're doing trying to find omega A,
Yeah.
do you just take the integral, but instead of you would have like a constant, that constant would be your initial?
That's exactly right. Yep. So raise your hand if you kind of got what Shane was suggesting there.
Wait, what did Shane suggest?
Yeah,
Alright.
so what I was saying was I set up radius of A times omega A equals negative radius B times omega B. And for omega A, you take the integral of alpha A. And instead of like we were doing last time, now there's a constant. And that constant that comes out of the integral is just your initial omega A.
I didn't know any better. It sounds like copying my paper.
All right. Are you guys practicing good social distancing? You're not sitting
No.
next to each other? All right. So let's go through this one then. I have a small gear A and I have a large gear B. And I know that RA times the change in theta A must equal RB times the change in theta for B. And then you can just start taking time derivatives of this thing because the radii are constant. So it's going to say RA omega A equals RB omega B, and RA alpha A equals RB alpha B. Because the radii are constant, when you take time derivatives, that's just going to go through. The problem tells me that alpha A equals 4.4 time cubed radians per second. Yeah, all right. That should be the, let's see. It should be radians to the seconds to the negative fifth power. So that when you plug in something with units for time, it comes out right.
Wait, Sean, can you write this out on the whiteboard or anything? Or
Oh. I am. Thomas,
Oh,
weren't you paying attention? Yeah. Sorry about that. I was doing exactly that. Son of a bitch. All right. This online stuff sucks. All right. Let's try that again. I've got my two circles. I know the arc lengths are the same. And I just start taking time derivatives. So the time derivative of theta is omega, and the time derivative of omega is alpha. The radii are constant. So when I take time derivatives, they don't change. Okay? Raise your hand, I guess, if that's clear, what I'm doing there.
second, let me copy this. Okay.
Alex, is that okay? Same.
Okay.
All right. So then, okay, so I can go from alpha of A to alpha of B, and then I can just integrate things up to get delta theta. So I can say alpha of E equals,
And Sean, how about the minus sign?
oh, thank you. I wanted to go through that explicitly. Good. So A, it says, is rotating clockwise from the diagram, which means that B is rotating counterclockwise. So let's think about minus signs here. That means that there's a minus sign on each one of these. Is that okay?
So one of my questions is, so even though it's counterclockwise is positive, why do we put a negative there? Does it just not matter where you put it?
Oh, it doesn't matter because I can multiply everything by -1. And it just moves
Okay,
across.
that makes sense.
It doesn't matter. All right. And then, so that tells me though, now I've got to think about this. From the diagram, they say it goes, alpha A goes clockwise. So that means that there actually should be a minus sign there in your formula. So it should be -4t cubed. All right. So now going back to this line, if I know alpha for A, I can find alpha for B. So that's going to be minus RA over RB times alpha for A, which is going to come out to be RA over RB times positive 4t cubed. So alpha B will come out as a positive number. Is that okay? Raise your hand if that makes sense. Or if you want me to go over it, say something.
Yeah, that makes sense.
Okay, so if that's the case, I can integrate with respect to time to get omega B. And that's going to give me RA over RB. I integrate that. Oh, sorry, hold on. So I want to find omega at time 2 seconds. So I'm going to integrate from 0 to 2. And then that actually gives me the change in omega. So I have to add a plus c, a constant. And that's going to be the initial angular velocity of A. So let me hold on. Hold on 1 second here. Let me be a little bit more careful. I tell you what I'm going to do. I'm going to keep the minus sign out front, and I can write this as minus 4t cubed dt plus the initial angular velocity of v. So that's going to be plus 20. Sorry, it's minus 20. Because it was moving, now alpha was clockwise and so was omega. There you go. So this piece right here, after I do everything, is going to be omega a at time 2. So this is the integral of alpha a dt plus the initial angular velocity for a, which was a negative 20.
Why would you add the initial? I don't understand.
Well, the integral of alpha dt gives me the change in omega.
Okay.
So omega at time 2 seconds is going to be the integral of alpha dt plus the initial angular velocity. It's like you're adding the constant plus c when you do the integral.
Okay.
Yeah. The integral only gives you the change in quantities, not the actual number. And I was worried about minus sign, so I kind of kept this minus sign here explicit. So then this whole thing is just omega a. All right. And then I want to integrate again to get the change in the angle, or change in theta for b. So I have to I integrate this. Oh, stop. Before I do that, they want the actual number at time 2. So let's do this thing. So I'm going to get minus RA over RB. I do that integral, and I'm going to have another minus t to the 4th minus 20. Okay, so that's my formula at general time, t, or omega b. And if I plug in at 2 seconds, the minus sign up front combines with the minus sign on the inside, and I get 12 radians per second. Okay, so that's what I get for omega b at 2 seconds, is 12 radians per second. So take a second, make sure you get that. While you're doing that, I'll erase what I have on top of the board.
No, you don't integrate the 20. It just like
No,
says,
right? Because it's saying the change in omega is the integral of alpha dt. So then that's omega of 2 minus omega of 0 equals integral of alpha dt. So omega of 2, the thing we want, is the integral of alpha dt plus omega of 2, or omega of 0. So separate from the integral. You add it after the fact. Okay, so that's, but I need this formula when I want to work out the angle, the change in angle for B, that equals the integral of this as a function of time from 0 to 2. So I need this form of it where t is still expressed explicit. And now I'm only finding the change in theta, so now I don't have to add a constant. I just work out the integral only. So that's going to be minus. Well, I can distribute this across, and I get RA over RB times the integral of t to the 4th plus 20.
Is that negative RA over B?
I went ahead and distributed the minus sign across to make everything positive.
Oh, okay.
Yep, good question. Yep. So that's just going to be RA over RB times t to the 5th. Wait a minute. Let me give you guys each a chance to shine. Because I know how much Sam loves integrals. So I'm really doing this for Sam. That's okay. It's called revenge, Sam, for all your comments in physics 2. So take a second, do that integral. Okay. It's a sum of terms. So the integral of the sum is the sum of the integrals. Each one is a power law. So this becomes t to the 5th over 5, and this is a constant, so it just becomes linear. So I get t to the 5th over 5 plus 20t. And I have to evaluate it between 0 and 2 seconds. And when I did that, I ended up with 15.5 radians. It's for delta theta 4b. Okay, is that, did anyone else, did everyone else get the same answer? Raise your hand if you got the same thing. I could have messed it up, but I don't think I did. Kirkland did, okay, Arnaldo did. Yeah, right, Sam. All right. Okay. Okay. Okay, I have another problem that this is not from the book, but I think it's a good one. So, we have the following situation. There's a wheel here and another wheel here, and we've got a rope which goes over the top without slipping, and we have a block C, and we're given an initial velocity which is down, and we're given an acceleration of the block which is up. And I'm going to say the radius of, this is pulley A, and this is pulley B. The radius of A is 600 millimeters, and the radius of B is 400 millimeters, and VC initial is 1,000 millimeters per second. Down, so it's actually negative 1,000. And the acceleration for C is 100 millimeters per second squared. All right. And there's a point D right here. And I want you to find my marker's dying, right? Worst time. Find,
Wait, so Sean, you're saying that block was like originally just like falling, and then someone just
acceleration going up. Yeah.
okay.
So there would have to be torque on these wheels.
Yeah.
But we don't know about torque yet, so it's not going to be problems. Okay. So what I want you to do is to find the acceleration of D at time 8 seconds, and find the the number of revolutions for A after 10 seconds. So find the acceleration for D at 8 seconds and find the number of revolutions for A after 10 seconds. Okay? So I'm gonna go, I have to help my son here for a second, but I'll be back. What I want you to remember, so point D, what kind of acceleration does it have?
Angular?
It'll have angular acceleration,
Nope.
yeah? So that's going to turn into a tangential acceleration. But it's on a circle. If it's on a circle, you also know it has what?
Angular acceleration.
Well, angular acceleration is about speeding up or slowing down as you go around. That's tangential acceleration. You also have centripetal acceleration,
Oh,
right? So the acceleration at D is going to have two pieces. It's going to have a
normal.
tangent and normal. Or I usually call them tangent and radial. Okay, so you want to find both the tangent and normal components of acceleration after 8 seconds. Okay, so I'm going to take a step back. I want you to work on that for a couple minutes here, and then I'll come back and help you. Sorry, guys. I realized I was supposed to hook my 5-year-old up to a Zoom class meeting 10 minutes ago. Sorry. So what do you think? Who's stuck? Raise your hand if you're stuck.
I'm stuck. So I just work the formula of alpha times r for tangential acceleration.
Good. Raise your hand if you, so alpha times r gives you the tangential acceleration. Raise your hand if you understand that.
I do.
If what? Wait, what did you say? Sorry.
The alpha times r gives you the tangential acceleration.
Oh, okay, never mind. Yeah, I see that. It's the same. It's just the same as that equation that we were talking about before with the omega and velocity.
Yeah, it's just the same. The other thing is, what does the rolls without slipping condition give you?
Constant acceleration, constant alpha.
Well, so if you know the acceleration of c, how is the acceleration of c related to the acceleration, say, of a point on this wheel?
Same.
They have to be the same. Yeah, well, almost. The tangential acceleration has to be the same. So the acceleration of c is the same as the acceleration for
Oh, so
tangential
it's the same
acceleration.
thing. You gotta multiply it, right?
What's that?
So you just have to multiply it to find the tangential alpha acceleration. I mean.
You could do it that way, yeah, if you want to. So what I'm wanting you to see is that this number for the acceleration at c is the same as the tangential acceleration. And it never changes, it's constant.
Okay.
On the other hand, the velocity of this point has to be the tangential velocity of point D.
Wait, so Sean, so you're saying like since we don't know about torques yet, right? So, but you're saying that A is having like something that causes that acceleration, that acceleration like that.
Could be, yeah.
So B wouldn't have any effect on that value, say if it had a torque as well? Or-
Yeah, we don't need to know anything about B. If I wanted to work out the accelerations for points on B, it'd be a similar analysis, but the problem didn't ask for that. You don't need to know anything about B in this
So is
problem.
the tangential acceleration not dependent on time in this one because it's constant?
That's right.
So basically, we just need to find the normal acceleration of d and then find the magnitude.
Yep, that's exactly right. So let me kind of do this. Does everyone have the numbers? Make sure you have that stuff. I'm gonna.
Wait, Sean, can you just explain that one more time? Like, so the tangential acceleration is equal to the acceleration of the block. Why was that?
Because it's without slipping.
Okay.
Mhm. If they think of it this way, the motion of the block has to be the same as the motion of the rope. But if the motion of the rope wasn't the same as the motion of the wheel, they would slip relative to each other. So they must be the same.
Okay.
All right. So I'm going to erase this. Is that okay? Right now. All right. So here's how I did it. You can kind of. So what I said was the tangential velocity equals the velocity of c, which has got to be the integral of the acceleration at c dt from 0 to time t, some arbitrary time, plus the initial velocity of c. And that's just because the acceleration at c is constant. This is just the acceleration of c times time plus the initial velocity at c. Okay? Raise your hand if that makes sense to you.
Is this acceleration you're talking about just the tangential one?
Well, it's going to equal the tangential. They're the same. But right now I'm just talking about the velocity at c, and I'm finding the tangential velocity is what I'm really doing. I know already that AC equals A tangent because it doesn't slip. I already know that. What I'm really working, so that part's really done for me. It's always a constant. What I'm working out is A normal, or what I would call A radial, which is going to be V squared over R, RA. So what I need to do is use the acceleration of the block to figure out the tangential velocity of a point at point D. Okay. So I can plug in numbers here. Okay. I guess I should hold off here. Is that okay? Raise your hand if that makes sense, what I'm doing. Okay. All right. So then I'm just going to plug in numbers here. So for this one, I get the acceleration at point D at time 8 seconds. Well, okay. Now, if I think about that picture, the tangential direction is in the y direction. So I'm going to get 100 millimeters per second squared. That was the tangential acceleration in the y direction. And then I have to get the radial acceleration, and that points to the center of the radius. So that's going to be in the negative x hat direction. So I'm going to get minus, and I'm just going to get v squared over r, and this is my formula for v. So that's going to be 100 times time, which is 8 seconds. And then the initial velocity was negative, the problem told me, so that's going to be minus 1,000 squared divided by the radius, which would be 600 millimeters, and that's in the x hat direction. So this is just v squared divided by r at point D, which has a radius a. And time and evaluated at time equals 8 seconds. So I'm
Is
just
that
taking
formula just for the normal acceleration? Or is that for the total?
this is the normal. So it's the total is going to be. I just ran out of room, Shane. This is the tangent part is here. This is the normal part. I have to add them as vectors.
Okay, perfect.
So that's why I get a y hat and an x hat there. And so my answer here in component form equals 100 y hat minus 66.7 x hat, and the units will come out to be millimeters per second squared when I work that out. Okay, raise your hand if you kind of followed that logic. Any? Good, good, good. Mohammed, is that okay?
I'm still copying it. I think I could understand if I do the homework and stuff.
Okay. So what I was going to do is resolve this one using vector notation, just to kind of show how it matches with cross products and stuff from the presentation, the online presentation. I'm going to get the same numbers, so make sure you have these numbers. I'm going to rederive it using cross products and stuff. Okay. So I'm going to, Mohammed, do you have this written down?
Oh, yeah.
Okay. So I'm going to rederive it in kind of a fancy, make it look fancy, but it's really the same thing. All right. So if you think about it, so I have my circle and circle. So I'm going to say that the velocity at point D at time 0 is going to be a negative 1,000 millimeters per second y hat. So think, because this block starts out going down at 1,000 millimeters a second, which means this is going to start turning with a tangential speed of 1,000 millimeters per second. And if you think about it, that means this point is going initially down at 1,000 millimeters per second. And the relative vector of D relative to A, so that would go from the center of A to point D, that's going to be 600 millimeters x hat. Okay. So I have these two vectors here for the vector for these quantities, and then omega vector for A initially. Well, I know the speed of A, so that's got to be the magnitude of it's going to be V tan A divided by 600. And if you think about it, because this is going down, that means that I have a clockwise rotation. So when I want to make this into a vector quantity, I'm going to say this is in the minus, the axis of rotation is out of the board. So it's got to be minus z hat. Raise your hand if that makes sense. So if a rotation in the plane is going to have an axis of rotation which is into your eye. So it's going to be the z direction.
Where's the minus sign coming from that?
Well, because this is the initial angular velocity, so it was initially rotating.
Oh, clockwise. Okay.
Yep. But this is why you have to be really careful with your minus signs, because it's so easy to screw it up. And then alpha is counterclockwise, so that'll be a positive z hat thing. So that's going to be a tangent over 600, and it's positive. That's going to be plus z hat. So I plug in numbers here. I'm getting this one is for omega initial. It was negative 1.667 radians per second z hat, and for alpha it was 0.1667 radians per second squared z hat. So initial omega A initial is negative 1.667 z hat. Alpha is 0.1667 z hat. Raise your hand if you see where I'm getting that part. Mohammed, did you see that? Yeah, no.
Yeah.
Okay, so I'm going to erase this, and then I'm going to use the formula I had for acceleration in the present with the triple cross product. I'm just going to plug in all these things and see that it gives me the same answer. All right. So before I do that, I want to remind you guys that x hat cross y hat is z hat, and y hat cross z hat is x hat, and z hat cross x hat is y hat. And if you change two of them, you get a minus sign. X, y gives z, and then you make 6 swaps, and then it's to get the plus signs. And or sorry, if you swap an even number of them, you get plus sign. If you do an odd number, you get a minus sign. Okay, so my formula in the video online said that the acceleration at d would equal alpha cross r dA. So alpha cross the relative vector from A to D. This is the tangential component plus omega cross r dA. And this is the radial part. So this is tangent, and this is radial, or normal. So let's work that out. When you do the cross products, you might remember from linear algebra or physics 1. Let me finish this. I'm doing my last example, then we can have lunch, okay? So you can, when you have a vector, you can pull the scalar, the size of it out and just cross the unit vectors. So this equals, from alpha, I get a 0.1667 From R, I get 600. And then I have z hat cross x hat. That's for the tangent part. And then for the radial part, I get plus omega. Each omega factor gives me negative 1.667. I have 2 of them, so it's squared. And then I have a radius of 600. And then I have to do z hat cross x hat. Okay, before I go through the cross products, do you guys raise your hand if you see where I'm pulling these pieces? Nobody, but just give me a second. All right. So now, okay, so now you have to be able to picture this. So z hat cross x hat, z hat cross x hat is y hat. So the first line, and you multiply that out, and sure enough, you're going to get 100 millimeters per second squared y hat. That's what I get from the tangential part. And for this one, the number, the size of it is the same. Oh crap. The omega I gave you is the wrong number. I gave you the initial angular velocity. Omega A after 8 seconds equals 0.33. I'm sorry.
Sean, can we finish this later? Because
Right.
the class is already done.
All right. Well, I tell you what. I posted a video, or I've got a video of this thing solved. So I will post that online, and you guys can watch it there. Basically, this is going to give you the same when you pull it all together using the correct angular velocity. This is going to give you the 66.7 x hat when all is said and done. Okay, so it's going to give you the exact same answers we found kind of doing it with the physics 1 approach. All right, so I'll have that in the video. Okay, I will let you guys go. All right. See ya.
See ya.
See ya.